So dark energy is the energy required to accelerate the universe away from itself. So by looking at standard candles, supernovae, they assume that these all explode with the same brightness. And they noticed that ones further away are dimmer than they should be, which implies that the universe is accelerating away from itself. And they've calculated this acceleration, and it turns out to be about 2 times 10 to the minus 10 meters per second. That's exactly the same acceleration that the Pioneer anomaly had, galaxy edges have, globular clusters have. It's the same acceleration. I can predict it very simply from my theory.
Mike, how are you?
Fine, thanks. Yeah, I'm fine.
Thank you for coming in. Very excited about this. We've made of this show, 50? We've probably made 50-ish episodes now. And 2 are standout for me. So my opening show was my friend Matthew Pines. We did one all about aliens, whether they're here or not or real. But when I about a month and a half into making the podcast, I watched Interstellar with my daughter, and I was trying to explain time dilation to her, and I couldn't. So I got her to listen to a Paul Sutter. I call him Sutter. You called him Suter. I got her to listen to one of his podcasts. And we got some of the way, so I emailed him, said, do you want to come on the show? Come out to the UK? And he said yes, and he came out. We made an amazing show. That one went out, and somebody emailed me and said, oh, you've got to talk to Mike.
Oh, it was after that one. Yes, I did see that one.
Yeah, they said, you've got to talk to Mike. Mike's got this incredible thesis, idea,
an
concept.
Alternative to what Paul Sutter was talking about. It's an alternative way to think about those same things.
Quantum inertia.
Yes, or quantized inertia.
Quantized inertia, right. I'm going to ask lots of questions and get you to explain it simply for me. But give me the simplest explanation of what quantized inertia is and why it is something we need to think about.
Yes, so up until now, inertial mass has been kind of assumed, the principle of inertia, that things keep going in a straight line unless you push on them. So there's never been an explanation for why that happens. So I've provided one, and I'll try and explain to you how it works. It's a bit complicated, it's very different, but I'm saying that things move because the quantum vacuum is not the same in all regions of space, and so it pushes on objects.
Right. Give me an example. Give me an object. Explain it in the environment, what we're talking about here.
Well, I can explain it in a simpler environment, perhaps, the ocean.
Okay.
Because I have an oceanographic background. I studied ocean physics for my PhD. And I did a lot of wave modelling at the Met Office for 10 years. And if you imagine a boat on a wavy sea, then, for example, if you have... so you've got this boat out at sea, and you put a skirt on one side of it to damp the waves. So it's got a skirt on one side, the waves are damped on that side, and the waves will push it from the other side, so it will start to move. Now, this is caused by an imbalance in the wave field. So there are more waves on one side than the other because of the skirt you've attached to the ship, and that makes it move. Now normally, what humans need to do to get things to move is to use Newton's third law. We have to use a rocket, so we push hot gases out one end of a rocket ship, and it moves in the opposite direction or takes off. But that requires a lot of fuel, a lot of danger, a lot of chemistry. This is a far gentler way of getting things to move. And I'm arguing that this is how nature does it. So instead of taking Galileo and Newton's idea that things just keep going in a straight line, because they're kind of lazy and they don't want to stop moving, what I say is that I combine relativity and quantum mechanics. So if an object accelerates to one side, say my hand accelerates to the right, then relativity says that information from far to its left can't get to it, because information can only travel at the speed of light. So if something's accelerating away, it has a blank spot behind it over here. Very far over here normally, and also it's been shown from quantum mechanics that any accelerating object will see a thermal bath of radiation surrounding it, and this is called Fulling-Davis Unruh radiation, or Unruh radiation for short. And this is very interesting because acceleration accelerating objects see space surrounding them as being warm, but an unaccelerated object in the same space would see it as being cold. So the temperature things see depends on the acceleration they have. But the new thing I'm saying is that these horizons that open up over here, they damp these Unruh waves, just like the waves in the ocean are damped. So that means that this object accelerating this way sees a lot of waves out this way, but fewer on this side of it. So it gets pushed back against whatever acceleration it had. And I managed to show in a paper and using the appropriate mathematics that this predicts what we know to be inertial mass. So it explains inertial mass for the first time in history.
Okay, so I don't know what inertial mass is. But is this to do with... So there's that question to do with the universe of their calculations based on the mass of each galaxy, or the mass of the universe. It doesn't add up, so they've referred to dark matter as a way of, I don't know, filling the gaps in their algorithms.
That's right, yes. Yeah. So, and this accounts for that, because the model I've just proposed is very similar to what we had before for inertia, but there's a tiny difference, which is like 1 part in 10 billion difference. It's very slightly different. And it turns out that, how can I explain this? Okay, so you've got these waves, this asymmetry between the waves on one side of the object and the other. If the object is accelerating extremely slowly, then these Unruh waves get as long as the cosmos. So you just can't see them. And I'm a very strong follower of Ernest Mach, who said that if you can't see something, then it doesn't exist.
But this is what I've thought about dark matter, dark energy. So I understand, in my simple world, the thesis, in that they've tried to do these calculations of what they believe the mass of a galaxy should be based on its rotation. Is that correct?
That's right, yes. The edges of galaxies are spinning far too rapidly to remain bound gravitationally to the galaxy. So they're going at about 200 kilometers per second.
So the answer to this has been there has to be some other matter that we can't see, that we haven't been able to discover. We'll call it dark matter, and that solves the problem. Yet nobody's found dark matter or can prove it exists, but that neatly plugs in and solves that equation.
Yes, that's right. Yeah. So they've been looking for this for 40 years, since about 1980, and they haven't found it. And they've spent a lot of money doing it.
No success at all. They found nothing.
Nothing at all. No.
But and the idea is, it's a particle that must have mass, but
yes,
we can't see it.
That gravitational mass, but it doesn't interact magnetically, so it doesn't interact with things that way, so we can't see it.
Hold on. So something has to react electromagnetically for us to see it.
Yes, that's right.
What?
Yeah, because light is an electromagnetic wave.
Okay. So it has to react with an electromagnetic wave to be seen.
That's right. Yeah.
Is there anything we have in the universe we know that anything else that we know doesn't react electromagnetically?
We have some small things. I guess you could say neutrons don't, but there's nothing that can fill that gap except some theoretical predictions such as axions, neutrinos, black holes. Although black holes you could possibly see simply because they're a black dot in the middle of the universe, but there's nothing that can account for the difference, the error we see in the galaxy rotation.
And there's nobody come out and said, well, hold on a second. We can't just have the answer be dark matter. We can't just say it's a thing we can't see. If we can't see, it might not be there. Something else, there can be another thesis. There can be another argument.
Yeah, so in the 80s, the first attempt at this was by Mordecai Milgrom from Israel. And he said, okay, maybe Newton's laws are slightly different. But he was a bit non-specific about how they might be different. But he proposed a hypothesis called MOND, Modified Newtonian Dynamics, which said that either the gravitational attraction of the edge stars of the galaxy is stronger than we expect, or their inertial mass is lower. than we expect. But this has been quite out on the fringe for a long time, and he didn't produce a model for it. He just said maybe this is true. But yeah, I loved that, and I started to think about it, and it turns out that the model of inertial mass I've suggested produces exactly the right outcome to correct the galaxies.
Right, we're going to come to that. I'm still on the point there's a lot of great, intelligent scientists around the world, brilliant people. Are there many at the moment who are saying, oh, hold on a second, dark matter might not be a thing? We might have got this wrong. Because it seems like it's almost like, it feels like it's an accepted answer. People will just say, there's dark matter, we just haven't found it yet.
Yes, you're exactly right, yeah.
But why alongside that isn't like, well, you know what? There may be no dark matter, therefore we need another answer. It just doesn't... It feels like the way consensus is there's this dark matter that we haven't found, and that's acceptable.
It's a strange situation. It seems that the media don't really go into it very deeply, but when I speak to actual astrophysicists, they're quite open to the idea.
Oh, so in the community, people are
not openly.
Oh, I know.
It's quite interesting that if you talk to them in private, they say they don't like it, but it never seems to get into the magazines and on the news.
Is that because it's... I don't know. There's risks with maybe publicly talking about it, or the people who run the magazines aren't the smartest.
I don't know. I wouldn't like to say, but
let's say, help me understand the problem they're trying to solve. Because all I know, it's something to do with the galaxies rotate. I don't know why they rotate, why they have to rotate, but they do. And because of that, when they add up the mass of a galaxy, they know there isn't enough stuff there for it to rotate at the speed it's rotating at. That's
okay. Well, the reason they rotate is that every time you have an object that forms and condenses gravitationally, whatever small angular momentum or spin it has is magnified as it gets concentrated into a smaller volume.
Okay.
Like the old idea of a ballet dancer who spins around but then draws her arms in and she spins more rapidly. Yeah. So that's why galaxies spin. But they spin far too rapidly, so that there's a certain amount of matter in every galaxy that we can see. We sort of count the suns in each galaxy and we say, oh, there must be that amount of matter because our sun is that mass and it has that luminosity. And you multiply it up and you can work out the mass of the galaxy. So that gives you the gravitational force inwards. And then they look at the stars orbiting around and they look at the Doppler shift of the light coming from them. So if they're moving away, the light is red-shifted, and if they're coming towards us, it's blue-shifted, so they can work out the speed that the stars are orbiting with. And they can work out the centrifugal force, the inertial force pushing them out. And that's much bigger, many times bigger, than the gravitational force holding them in.
And they've done that on multiple galaxies?
Yes, almost every galaxy. I think they've found 4 that are normal. But they may have got the distance and mass wrong for those anyway. So it may be that none of them are normal.
Interesting. Just out of interest, do they all spin one way or can they spin any way? Can they spin both ways?
Oh, that's an interesting question. They do tend to spin together. Statistically, they do tend to spin together, which is interesting.
Yeah. Huh. Okay. And just working back through this, so they've done the equations, they've tested it on multiple galaxies. And there's this gap. There's this large, significant mass gap. And the assumption is that within galaxies, there is this dark matter.
Yes, around the halo, sort of around the edge of them.
Around the edge of the galaxy?
They have to put it around the edge of the galaxy, yes.
Because the force has to come from the edge? Why can't it be all through the galaxy? Because
the only stars, and this is very interesting, the only stars that are behaving oddly are beyond a certain radius.
Okay.
So around the edge.
In what way are they behaving oddly?
They're orbiting too fast.
Oh, it's just the stars at the edge are orbiting too fast.
That's right. So in the middle, they're fine. We can predict those really well. But
is it the further out they are, the more odd they react, or it's just the ones on the edge?
There's a particular radius at which it begins.
Okay.
Abruptly.
Interesting.
And that's very interesting as well, because I can predict that as well, that particular radius.
Right. So you were looking at this one day, and you went, "I'm not having this dark matter. I'm not believing this." How do you get to the point where you say, "I'm going to propose an alternative to this"? How does that even happen?
Well, I've been thinking about inertia for a long time, and I've been modelling these ocean waves, and making analogies. And what I actually noticed first was an anomaly called the Pioneer anomaly, which is controversial now because there's somebody who thinks they have a thermal explanation for it. But the Pioneer 10 and 11 craft were launched back in the 70s, and they went out through the solar system. And because they used spin stabilization on them, so they were spinning as they went along. And because of that, they didn't need many firings of their rocket to course adjust. So it was the world's best ballistics experiment, if you like, these two spacecraft. And they found this very strange anomaly, that they were a bit too much attracted to the sun than they should have been, by exactly the acceleration by which the galactic edge stars are a bit too much attracted to the galactic center. It's the same number. Well, it's very close. So I became fascinated by that, and I managed to explain the Pioneer anomalies with this wave model of inertia by saying that, as I said before, if you've got a thing accelerating, it sees Unruh radiation around it. But on the side it's accelerating away from, it has a horizon, sees a horizon, so there's fewer waves there, so it gets pushed back.
So, okay, let's dumb this right down. When you're talking about waves, what are these waves that it's seeing, not seeing?
Okay, so Unruh waves are, it's thermal radiation, so it's just like heat, really. And it's caused by horizon. So if you think about, I don't know if you've heard of Hawking. You've probably heard of Hawking radiation.
Yeah.
So you have
they're the jets that shoot out of a black hole.
That's a slightly different thing.
Oh.
So if you have a black hole, there's a lot of mass in one particular area within the Schwarzschild radius. Paul Sutter was talking about this. And you have the event horizon, and there are quantum fields everywhere.
Okay.
Oh, yes, very good. Quantum fields everywhere, but the difference is that right on the event horizon, if you get a virtual pair of particles created, one of them will go into the black hole and be lost, and one will come out and be seen. Now, normally these virtual particles, these quantum particles appear and recombine, appear and recombine all the time. It's like a quantum foam. But on the edge of a black hole, as soon as they form, one gets stolen by the black hole. So this one is free to leave. And so you get radiation coming off the black hole, and this is the Hawking radiation.
Okay, we're going to have to again go back a step. What do you mean by virtual particles? Because I'm thinking the word virtual.
Right. Okay. So this comes from Werner Heisenberg back in 1924 or so. He said, he proposed his uncertainty principle that states that the smaller volume of space you look at, the more sure you are about your position. So the less sure you must be about your momentum. So that means that on smaller and smaller scales, as you look closer and closer in, there must be virtual particles appearing all the time.
Virtual particles of?
All sorts, all kinds of particles just at random appearing.
And appearing from where? How do they come into existence?
They come into existence in pairs, so it conserves energy and mass and charge and all that kind of thing.
No, I'm just wondering how does something come from nothing? How do they just come to exist?
Oh, well, that's an interesting question. Yeah, well, nobody knows.
But we've seen it. We can observe it.
We've seen it, yes. It's been tested quite well now. It's a major part of quantum mechanics. So you have this quantum foam.
Okay.
And a horizon, the beauty of a horizon is that it's able to split these two things. They form quite innocently, thinking they're going to join back together again, but then the horizon yanks one of them away, and one is left, so we can then see it. And this is where the Hawking radiation comes from.
Okay, I'm following.
But it doesn't just happen for black holes. It happens for anything that accelerates. Because if you accelerate, Einstein says you see a horizon. As I said before, so as you accelerate away, you see a horizon, because beyond that you can't collect information anymore.
Mm-hmm.
You're accelerating away from it. And this horizon too splits virtual particles. So you get a kind of Hawking radiation come off it, which is called Unruh radiation.
Okay. Is that a new theory, Unruh radiation?
It was first proposed in 1973 and by Unruh in 1976.
Okay.
So it's been around for a while, but it was only actually seen about 2 years ago by a guy called Lynch, who actually emailed me
Okay.
when he'd seen it excitedly to say, you know, this Unruh radiation you use in your theory, I've just seen it.
Okay, and that's been shared widely. It's accepted now.
It's more or less accepted by most physicists. I think that they have now seen it.
How do you spell that? UNRA.
Yes, UNRUH.
Can you look out, Con? I want to have a little observation on what people say about it. And the role that Unruh radiation plays back into your thesis is...
So, yes, you have this object accelerating. It sees Unruh radiation all around it. There's a horizon on one side, the side it's accelerating away from. This horizon, the new thing I'm saying is that this horizon damps this Unruh radiation. So there's a lot of radiation in front, there's less behind, so it gets pushed back against this acceleration, which accounts for inertial mass.
Huh. Here we go. Physicists propose new methods for observing hypothetical Unruh effect.
That's a hypothetical one. If you look for Lynch, LYNCH, acceleration-induced thermality.
Where's he based?
He was in Israel, and then at CERN.
Okay.
So, yeah.
Yeah. I'm so out of my depth right now, Mike. I'm trying to wing it with you. Here we go. Does that make sense to you, this chart?
Yes, so the chart shows a lot of dots, and that's his data.
Yeah.
And the expected Unruh radiation spectrum is the curve. So you can see the dots go along the curve, and so...
Oh, yeah, that's a thesis. Loads of equations.
There you go.
That's for the smart people, Con. Here we go. Right. So which one am I looking at? Which of the four?
The bottom left is the most crucial one.
Okay.
So it shows the spectrum of radiation that was seen along the x-axis.
Yeah.
So high frequency to the right, and then it shows the intensity of the radiation at each frequency up the y-axis.
And then you can see it really slow down. Like,
well, you can see the dots there show roughly the same shape as the curves, which are the theoretical expectations for Unruh radiation.
Okay, so if we go back, I'm sorry, having to do this really in a really simplistic way. If we go back to explain this in terms of the dark matter problem with the universe, what does this solve, and how does it solve it? And as simply as you can explain it, please.
Okay. Yes. So we have this model of inertia. So radiation on one side, less radiation just gets pushed back. But if your acceleration is very low, then the horizon moves further and further back as the acceleration gets lower, until eventually you can't see it anymore. It might as well not be there. And then this mechanism for inertia it vanishes, because you can't have a difference between the radiation on this side and this side anymore. It's now the same, because there's effectively no horizon on this side anyway.
Okay. So
I'm predicting that inertia will disappear at very low accelerations.
Which explains why there's that radius.
Yes, exactly right.
Yeah,
yes.
The radius explains why past that radius.
That's right. So at the edge of galaxies, where the accelerations are very low, inertial mass and the centrifugal force pushing out disappears. Just disappears. That's what I'm proposing. Okay.
So you've proposed this.
Yeah.
What does this break in terms of physics, and who are we going to piss off?
Yes, it's
there's a few egos. If this is correct, you think it's correct, or you believe it's correct?
20 years ago when I was first starting, I wasn't particularly confident. Now I'm rock solid.
Okay.
So I'm very confident about it because it agrees with so much. And I published 27 papers, 4 books, and tested it on many observations. It violates the equivalence principle, which is the supposed equivalence of gravitational and inertial mass, which is the basis of general relativity.
Okay, so you're breaking Einstein.
Yes.
It's a bold thing to do, Mike.
Yes, but I'm doing it in a way that could not have been seen in the lab. Normally, they test the equivalence principle by effectively dropping 2 balls of different weights off the Tower of Pisa, as Galileo did. It's far more sophisticated now.
And they fall at the same speed.
And they fall at the same speed, yes. And that's the equivalence principle. What I'm suggesting would still have them falling at the same speed, but both an equal amount faster. So it won't show up in the tests that they're all doing for the equivalence principle. So I've done it in a way that is still consistent with all the experimental results. What I'm suggesting also breaks, and this is very slight.
Hold on, let's stay on that. So it's just stay on relativity. Yeah. If it breaks that, does it fundamentally break relativity, or is relativity can it coexist alongside relativity? Like, does E still equal mc squared?
Oh yes.
Okay.
The changes are relatively small, unless you have a very low acceleration. But I'm proposing a new form of general relativity that fits more with what I'm doing than the curved space-time of Einstein.
You fix a relativity.
Yes. Because one way to look at the galaxy rotation problem is that general relativity has not predicted a single galaxy rotation.
The humble bee, a keystone species crucial to the survival of Earth's inhabitants. Here's how things would look if bees vanished. And here's how they'd look if humans vanished. But imagine if instead we became a keystone species by doing things the right way, by taking responsibility for our actions and becoming the solution. Iron mines the world's most responsible currency the right way. Because the future depends on it.
Oh, so there are. Okay, so it's interesting because, again, in my limited understanding, I know Newtonian physics took us so far, and Newton's highly respected in the history of time.
Oh yes, yeah. And so is Einstein, and quite rightly so.
And some other people. Maxwell's a guy I keep hearing about.
Yes, yeah.
But there came a time when there were limits to Newtonian physics, and without you even doing this work yourself. Relativity is, generally understood and accepted, but it's generally understood and accepted with some quirks. Like, okay, relativity breaks down here, because I know there's been a difficulty in marrying the worlds of relativity and quantum, right? That unified theory of everything hasn't worked. I know about Einstein's quote saying it's spooky at a distance, yada yada. So nobody's unified everything. So there are these challenges. I understand that, but how does it work in terms of a thesis? We use it as much as we can, but we know there might be fundamental issues with it.
I think it's widely accepted that either quantum mechanics or relativity are flawed.
So one of them's flawed.
Yes, that's right. And I'd say it's relativity that is more flawed than quantum. I'm also violating, and this is very slight, Newton's first and second laws. Because Newton...
Explain what those are for people.
Yes.
I mean, I know.
So Newton's first law is the law of inertial mass, that things keep going in a straight line at a constant speed. But I'm saying there can't be a constant speed. there has to always be a very small acceleration, which is incredibly small. It's 2 times 10 to the minus 10 meters per second, which is incredibly slow.
But that's no different to Einstein coming along at some point saying there's no reference point. That's all he did. He came on and said, we thought this, but now we think this. There's no reference point.
Yes.
For relativity, you're basically saying you're just slightly correcting something.
Yeah, he corrected it for fast speeds.
Yeah.
I'm correcting it for low accelerations.
Okay.
So, and he corrected it for speeds because technology was moving humanity into that regime of radio broadcasts and that sort of thing. So that's why it was noticed. I'm correcting it for low acceleration because we've now looked into deep space and we've seen low acceleration things like galaxies which don't fit. So we have to update again.
So you're kind of fixing it. You added some nuance.
Yes, although I wouldn't say it's quite fixing, because that implies I'm kind of cheating. But what I'm trying to do is what I'm suggesting. There's only one prediction it can possibly make, and it turns out to be the correct one.
Yeah.
So the model I've suggested doesn't have adjustable parameters. There's only one way for it to work. It only predicts one thing, and that turns out to be what's observed. So
it's either that or we make up a particle no one knows exists, can't see, can't prove, can't test. I mean, it sounds like a fair alternative.
Well, I can say more against dark matter. It cannot possibly be true.
Okay, let's do this. I want to hear it.
Because, okay, so in order to get dark matter to explain galaxy rotations, you have to put it around the edge. But why doesn't it fall into the middle then? You have to specify some physics which forces it to stay out at the edge.
Okay, so you have to accept there's a thing we can't see, prove, test, and it has some unique physics.
Yes, exactly.
It's starting to sound like bollocks, man, isn't it? That's the title of this show, Con. It's going to be Dark Matter as Bollocks. Okay.
So, if that's true, why not see if there's something that looks like the galaxy rotation problem on a small scale? And it turns out there is. If you look at a globular cluster, which is a small collection of stars and a kind of ball inside a galaxy, they show exactly the same effects. At their edges, their stars orbit too fast.
Huh.
Or wide binaries, stars exist in pairs orbiting around each other. And the ones that are far enough apart show exactly the same fast speeds that the galactic edge stars do.
And sorry, just to keep repeating myself, under relativity, none of these things should happen, under the laws of relativity.
Well, under the laws that they've applied to dark matter, which is required to make relativity work.
Yes.
So, and also even our nearest neighbour in space is embarrassing standard physics, because Proxima Centauri orbits far too fast. So physics can't predict that either.
I love that we've just made this thing up and had it widely accepted just to make our calculations work. Yes. Well, let's just invent this dark matter. We'll just say it must be there. If we can't prove it, we can't see it, but we'll just say it's there, and then all our calculations work. Are there other people who've worked on this outside of you, prior to you even looking at it, or are there other people just working on similar things?
Well, I've mentioned Mordecai Milgrom, who first suggested MOND back in 1983, but he didn't have a model for it, and he had an adjustable constant in his theory, which I don't have, so he had to fit it to the data. But he said a useful thing that maybe Newton's laws are wrong. There were 3 guys, Heiss, Schroeder, and Puthoff, who suggested a model for inertia back in 1994. I read the paper and I loved it.
Okay.
But again, they needed an adjustable parameter. They had inertia as an interaction between a body and the quantum vacuum, but in a different way to me. They based it on speed, and they needed an adjustable parameter. But that was also an inspiration to me, their paper.
Your first paper, you did 27.
Yes.
The first paper. What was the first paper? Like,
Oh,
when you
yeah.
do 27, are they revisions? Are you working hard at it, or is it different concepts themselves, or a mix of?
Well, I tend to work by writing a paper to test the theory on a particular observation.
Okay.
And normally, people with new ideas, they find it hard to publish papers. But because I've always shown that only what I'm suggesting can predict this real data, the journals have found it hard to reject me. I submitted my first paper from the Met Office, actually, and the reviewer was quite amused by it, because instead of saying I predict this, I predict that, I used the word forecast all the time.
Okay. So how have you been received by the scientific community? Like, what? Give me the spectrum of, because I'm sure there's some people who've warmed to the ideas, but also there's some people who maybe have rejected the ideas, and that can be a combination of maybe they reject on science, or they reject on ego, or they reject just whatever. How's this experience been?
Well, at first, I don't think they really knew how wide. They didn't really know the magnitude of what I was doing, I think. So for the first few years, it was fairly quiet. But then I started to, and I had a few people interested. I was invited to conferences, that sort of thing.
Okay.
But then I started to bring it down into the lab. I started to say, well, if this is true of inertia, we can actually do things with this. And I started looking at things like Pokletnov's disks, the M drive, and capacitors. And at that point, it became quite hostile. I mean, my papers were banned from the archive, for example, which is all physicists. Some journals you have to pay to read the papers, but there is a physics library called the archive that stores everything that everybody can read for free, which is a great idea. And all physicists look there, and I was publishing on it, but at some point I was banned.
You got cancelled.
Yes, I was cancelled.
Hold on, the M drive, is that the idea of a thrustless accelerator?
Yes.
That's like this utopian idea that you could build a spacecraft without the requirement for fuel to thrust.
Yes,
and so
right.
It's an idea that people love the concept of, but has been by certain people considered debunked as it's not possible because we're wedded to the theory that we need thrust for acceleration.
That's right, yes.
Proud of myself there, by the way.
Yeah, very, very good. Yeah, but I can predict the M drive and other things as well.
Do you think that's the M drive is why is the issue? That because what you're proposing therefore legitimizes the M drive. Do you think that's the reason people have pushed back against you?
Yes, I think that's a good point, because it looks reactionless.
Mm.
So there's nothing coming out the end to push it.
Yeah,
and that is beyond standard physics. But I'm saying that there's this Unruh radiation we've never seen before, which is there. And the M drive, because it's a tapered cavity, it damps the Unruh waves more at the narrow end than it does at the wide end. So the M drive will move down towards the narrow end as it does, and I can predict the thrust that was seen by Roger Scheuer, who came up with the M drive.
Okay. Just out of interest, on the M drive, can you scale the concept to have something that can therefore then accelerate at super fast speeds across galaxies, or is it just an idea of something that can work it only works slowly?
Well, at the moment, engineering-wise, it only produces a thrust of only a few millinewtons, so it's a very tiny thrust. But the great thing about having a theory that explains it, like quantized inertia, is that you can see how to enhance it hugely.
Okay, I'm going to come back to the M drive. I just want to work through this logically. So going back to the responses from the scientific community, you've got cancelled in one area. Have you been like certain people try to ridicule you?
Well, yes. There've been a few bad articles, I guess you could say.
In what way?
Well, what was his name? Brian Koberlein.
Should we try and find that one?
Yeah, he wrote something about quantized inertia, which criticized it severely, but it was based on his not understanding the theory.
Okay.
So,
who is he? What's his? Is he legitimate?
Yes, he's from California. I think he's American anyway, and he has some links with universities. And
does that make it hard or is that part of being writing papers? You have to accept there's people who will be criticising. You just get accepted.
It has been extremely difficult, yes, because if you're an academic at a university, you're expected to not only publish papers, but have people cite them.
Okay.
So your citations are added up. And if at the end of the year, everybody hates you and nobody's citing you, they say, they're not so happy.
Have you been cited? You must have been cited.
Yes, but not a huge amount, I'd have to say. So my university was asking. And then because I was talking about possibilities for thrust in the lab, DARPA started funding me.
Yeah. So explain who DARPA are.
Which saved me. So DARPA, the US Defense Advanced Research Projects Agency.
Mm-hmm.
So obviously they're connected to the military, and their aim is to make sure that America isn't surprised by any technological developments, that America will get to those developments first.
Mm-hmm.
So as soon as I started talking about the
so they're open-minded.
Yes, that's their job, to take a risk on things that are coming up that might be massive, but could fail, but might be massive.
Yeah,
that's how they think. So I started talking about the M drive, and they came to see me in Plymouth and invited me to apply for some funding. So I got 1.3 million to test for thrust in the lab. So that saved me, really, because it gave me 4 years of funding to work with.
Okay, I just want to go back to just stay within the area of. So are there noted, legitimate, credible people who think you're onto something?
Yes.
Okay.
Well, so I've swapped emails with the Astronomer Royal, for example, and he's open to it. Not necessarily a supporter, but he doesn't think it's nonsense. And DARPA obviously valued it as well.
But are there people who, are there legitimate criticisms which makes you question it yourself? Go, okay, that's a fair criticism. I need to prove it.
The closest to that will be a paper published by Michele Render, back in 2019, and he pointed out that I'd cut some corners in some of my theory, which I accept, but it doesn't make much of a difference to the final result.
Okay.
And I've since gone back and rederived it, bypassing these problems that he pointed out. So, but there's nothing. I've never seen anything proposed that it's always worked. Everything I've tested the theory on, it's worked really well, which has been an amazing experience, really.
Yeah, but must be frustrating if you think you're onto something. At least have people outside of DARPA, because they have an open mind and a reason to fund and justify this. But you'd want some people in the scientific community to come to you and say, "Okay, I think you might be onto something. Let's work together on this."
Yes, well, some have.
Okay.
There's a chap from Catalonia called Jaume Gine, who's at the University of Barcelona.
Mm-hmm.
So he's both published some papers with me, which was great. And Xavier Hernandez from Mexico. Alexander Unziker from Germany has been a great support, and I love his books. So yes, there are some.
Did we find Brian Koberlein? Do we know how to spell it? Do you know how to spell
Oberlein?
See what this joke has to say. Quantized inertia, dark matter, the EM drive, and
Yes, that's right.
how to do science wrong.
Yes.
God, that's a bold statement. Come on, Brian. Okay, so can you explain this chart he's got up here? The rotation.
Oh, that's that's simply the galaxy rotation problem. So the x-axis is the radius out from the center of the galaxy.
Yeah.
The y-axis shows you the speed in kilometers per second, and the dashed line is what the standard theory predicts, and the data is shown by the dots with error bars.
All right, let's see what he has to say. All right, science isn't easy. For example, Mike McCulloch's theory of modified inertia by a Hubble scale Casimir effect.
That's what I call quantized inertia back then.
Okay. McCulloch's model has been in the works since 2008, but it's become popular in recent years due to its connection to EM drive. Yeah, people want the EM drive to be a thing, right? You might recall that this is the device, according to its proponents, can create a thrust without any traditional propellant, which could revolutionize space travel, blah, blah, blah. It's created quite a stir among the public because of the tremendous possibilities of if it succeeds. I think the EM drive, even though some people think it's debunked, that is a more popular idea within science, right? Outside of your thesis, there are more people working on it.
But it gets people's backs up because it's radical.
The best experimental results can't be distinguished from background noise, and such a device would violate basic physics. McCulloch argued that the effect was not only real, but it could be explained in the context of his model. The basic idea is that inertia is caused by Unruh radiation. Inertia is a basic property of matter. That means the velocity of an object will remain constant unless a force acts on it. If it is the basis for Newton's first law of motion, so Unruh radiation has never been observed. Well, that's not true now. Would you say?
Yes, it's been seen twice now by Lynch.
Okay, but has he been peer-reviewed and been proven?
Yes, Lynch has been peer-reviewed and published. I don't know in which journal, but I think it was a good journal.
So is that at the point Unruh radiation is now accepted?
Yes.
But when he wrote this, it wasn't accepted. Okay.
That's correct, yeah.
Okay. But in quantum theory, empty space can be described as being filled with quantum field. A vacuum, in this view, is simply the lowest possible energy state for these fields. In most cases, empty space looks like a vacuum as we would expect, but for an accelerating observer, the field is an observed energy. As a result, an accelerating observer would be heated by quantum particles known as Unruh radiation. McCulloch argues that when an object accelerates, it interacts with Unruh radiation, which causes the object to resist a change in motion. Thus, inertia is an effect of acceleration rather than an inherent property of matter. Okay. There are problems with this idea from the get-go. For one, the Unruh effect in standard quantum theory is extraordinarily small. Well, you've said that.
Yes, but it's big enough. It's just the right size to produce inertia.
Yeah. If you accelerated 1 trillion times greater than Earth gravity, you'd only see a thermal temperature of 40 billionths of a degree above zero. Is that correct?
Well, it's something like that.
Yeah. Furthermore, since Unruh radiation comes from all directions, it couldn't create the effect of inertia on its own.
Yes, but he doesn't understand there that I've got a horizon on one side, which makes it asymmetric.
Oh, okay. But rather than be deterred by this, McCulloch adds other effects into the mix. Since the observable universe is finite, the wavelengths of Unruh radiation is limited, and combined with the cosmic Casimir effect and a bit of inflation theory can somehow produce the effect of inertia. The Unruh effect, Casimir effect, and information theory are all well established in modern physics, but they're hodgepodge. So he thinks it's a hodgepodge mix. That's the M drive there, isn't it?
Yes, that's right.
Yeah, I've seen that. Okay. However, even this isn't enough to explain the EM drive. In his paper on the EM drive, McCulloch argues that photons have mass and that photon mass varies with time. The time-varying inertia allows the EM drive to accelerate. The idea not only violates Newton's third law of motion, it violates special relativity, general relativity, and Noether's theorem. I mean, you are busting a whole bunch of physics here, man. Since these are all well-tested theories that form the basis of countless other theories, their violation would completely overturn all of modern physics. Well, that's what we're saying, aren't we?
Yes.
We're here to do that.
Exactly. Yes, that's my job as a physicist, really, to improve it. But it only makes slight differences to these theories in our regime. It makes big differences in deep space, low acceleration.
Yeah. So all those models have failed in deep space. They're proven as failed.
Yes.
Yeah.
I think they're falsified for sure because of the wide binaries and the globular clusters. And
Yeah, I mean, but so what we're saying is that Newton's laws of motion are kind of accepted. Relativity is accepted, but when they're tested in the deep parts of space where there's unusual circumstances, they fail.
Yes, exactly.
Yeah. And you're saying, I've got an idea based on Unruh radiation which answers this. Does it prove how many times have you tested this on multiple galaxies?
Yes, so I took the Sparks catalogue of galaxies, which contains 153 of the best observed ones.
Okay.
And I tested it on those, and it was perfect. It agreed perfectly.
Okay. I mean, also, it's kind of cool that you got somebody willing to go out there and actually debate this. You want the debate.
Yes, that's right.
Yeah. In the most recent work, McCulloch claims that, I'll just go with QI, can explain the odd behavior of rotating galaxies. It's long been known that galaxies rotate faster than expected. Given the amount of mass we can directly see in the galaxy, most of them should simply fly apart. The popular solution is the conundrum is that galaxies contain dark matter, but other ideas such as modified Newtonian dynamics have been proposed. Like MOND, quantized inertia proposes that the inertia of an object is less at small accelerations, so the weak gravity of galaxy can keep stars from flying away. Starting with an equation of modified inertia, the paper derives the predicted rotation speeds for several dwarf galaxies. It then compares observed rotation speed with the predictions of Newtonian gravity without dark matter, MOND, and quantized inertia. Newtonian gravity fails, as long as been known, and the other two models agree with the data equally well, though with uncertainties on the order of 30% calling data. Is that fair?
I'm not sure which paper he's reading there, whether it's my 2012 one or the later one.
And so McCulloch then argues that quantized inertia is inherently better than MOND, since MOND relies upon an adjustable parameter.
Yes, exactly, because you can adjust it just to fit. It's easy to do that, whereas I can't adjust mine, but it works.
Okay, never mind the fact that quantum inertia violates established physics. See, look, Mike, there's every chance we put this interview out and some people come back and say, don't talk to that guy, he's crazy, he doesn't know what he's talking about, we've debunked this. But I don't even like this idea of established physics, because all physics is established until new physics comes along and disproves it. And we know that. We know that from everything from Galileo to Newton to Einstein. I know that. So,
and every point physicists think that it's fantastic, but there's always a change coming at some point in the future.
And we know that the established physics breaks down. The established physics breaks down when measuring the spin of a universe. We know that, and the mass. And we know that the accepted answer at the moment is dark matter, which no one can see or prove exists. There's a bit of snobbery in physics, I think. Okay. By itself, this is pretty standard for a speculative paper. Here's a wild idea. It can kind of explain a strange physical effect. Maybe it's worth exploring further. It's a kind of what-if paper that could lead to interesting models. That's fair, but doesn't really prove anything. Sure, QI roughly agrees with the galaxy rotation curves, but so do a dozen other speculative models. Is that true?
Well, the models certainly, but all of them have an adjustable parameter of some kind, either dark matter that you add in or the parameter of MOND, A0.
So making shit up.
Yes. So I have a kind of philosophy that you should never put anything arbitrary in a theory. And I've kind of stuck with that.
Yeah, okay. I think that's fair. McCulloch claims on his blog that the model only predicts galactic rotation curves without dark matter. It predicts cosmic expansion without dark energy, solves the pioneer anomaly, and the flyby anomaly could be used to create free energy through... I'm not even going to try and say that word. What's that?
Sonoluminescence.
Sonoluminescence? Okay.
We can get to that.
So I'm going to put that one down. Sonoluminescence. It's everything we could wish for. These claims are iterated in popular press without any critical analysis. As a result, the model has built up a fan following who think that skeptical scientists are just haters trying to bury the next Einstein. Well, that's what they bloody sound like. But that's how science is done. To be viable model, QI will have to address its contradictions with established theories, and that will prove extremely difficult. Claiming victory is easier, but its approach will get you lost in the woods. See, it kind of reads... It doesn't sound like he's disproved it. It sounds like he's like swimming in a field of physics elitism, and well, Mike hasn't.
He doesn't like it.
Yeah, but like he hasn't. I don't know, Connor. Mike, how do you? What do you think?
I'm well lost.
Yeah, I think firstly, I think it's cool that he's debating this. I don't think he's done a very his argument is you're challenging established physics and there are other speculative models. They're not, to me, strong arguments. Do you know what I think it is? I don't think, tell me if I'm wrong here, I don't think it's the model he or others have an issue with. I think it's the consequences of it being right. It's the consequence that if you're right, EM drive is possible, and then solar luminescence, which also sounds badass, is also possible, and they break other accepted norms that people have come to based on the physics.
It could be that people think it's too good to be true.
Yeah. But in some ways it is too good to be true.
In a cynical age.
Yeah.
But sometimes things are actually good. So it is possible.
I'm going to go back to my thing here for a second. 1 second. Okay.
Did you write this, by the way? This article up there.
This one? Oh. Yes, I did, yeah.
What? How algebra cures wokeness. Oh. Okay, hold on. Maybe it's because the hard science is so unifying that there are... Oh my God, I got to read this for a second. Good find, Con. As a scientist, I of course believe in science, but that does not mean I believe what experts tell me. Science is the opposite. The belief that one should always disbelieve experts and check facts for oneself. Slowly over the last 30 years and quickly over the last 5 years, I've seen the West ban facts that were tested and proven and enforce what is factually wrong but non-offensive. Many people have noticed this and complained. It's pretty obvious, but they have been silenced. As a scientist then, how do I respond to the new Western fantasy movement? For me, it has meant rediscovery of the value of real. When I stub my toe, this reminds me that nature is not a product of my mind, and I can make mistakes. I'm not going to read the whole article. What?
This paragraph is good. But...
Which one? You found? Okay. In the evening, I watch old or foreign films. I gave up watching modern American films because the woke propaganda became too overt. Largely films from before the 1990 and the films from Eastern Europe who had woke communism for decades are not propaganda. The group targeted for humiliation appears to be the straight white man, so it's no surprise that almost every entertainment they love, Star Wars, Ghostbusters and Doctor Who, have been trashed by the woke, just as the Mexican temple of, how do you spell that,
Quetzalcoatl
was demolished by the conquistadors and a church built on top of it. When I help my son with his homework, we learn the subjects. We also talk about the woke propaganda in the textbooks. I want the school to teach facts without trying to mold my son's mind covertly this way, but it's hard to know who to complain to. Is it a soft revolution? There's no Lenin or Mussolini figure. Not anyway. It's hard to see where the impetus is coming from. So one has to respond, as I have shown above, by actions every day to stay based. I love this. What we now have is a war for what is real. We are being humiliated, a form of control, by being denied the right to say what is real, what has been proven. As a scientist who loves facts and algebra, I feel this very keenly. I'm responding by insisting what is real more than before. Oh, these are your ideas for a base day. I didn't know we were going to get this. Don't stub your toe. If you do, remember nature is real, opinion is not. Predict something real with algebra. Be wrong, learn, enjoy. Go for a walk to remind yourself what is real, what is not, and not digital fantasy. In shops, use hard cash. Arithmetic is another system that bases you. Take up art from life. It anchors you to reality, and it's satisfied as well. Consider a spiritual outlet to learn humility. No one humble is bad. Follow age-old social rules that allow useful freedoms in other areas. Watch old or foreign films. Hollywood is now manipulatively woke. Teach your children how to be based too. They are under pressure. Make a habit of saying, what's the evidence for that? Yes, I had no idea we were coming to this. That's amazing. That's quite funny as well. I got an email from my daughter's school from their head of I think they've changed it to EDI, Equity, Diversity and Inclusion, and she's preparing us for their EDI framework, which is coming. And at the time I thought, I don't need this shit. Can you just teach them math and history? I don't need you deciding what this is what I'm paying you for. I don't need this in their curriculum.
Yes, that's
We didn't
right.
have-
It's like the Soviet Union, isn't it? With
Well, we didn't have this shit when I was a kid.
Hmm.
We had debate. That was interesting. I remember when I was about, I don't know, whenever the first Iraq war was, 1990. So I would have been about 12 or 13. We had a debate and you had to pick a side and argue from that side. That's fine because we've been asked to argue and debate a point. And we all knew inherently, don't be racist because you're a dick. Just don't be a dick, right? We all knew that. We all knew racism was bad, but we don't have all this range of like propaganda bullshit rammed down our throat that certainly is happening now.
I don't like the fact that certain opinions are banned. It's not necessarily that I like one opinion over another one. It's just that I don't like the fact that they're banning some opinions.
Very important that you don't lose this, okay? This is your inheritance through Bitcoin.
Let Bitcoin rip. Don't rip up your Bitcoin. Set up inheritance with Casa.
That's crazy. That's a whole other subject we can come back to. But I do want to stick back to your thing. Yeah, I don't think, not because you're here, I just don't think Brian, all right, Brian, I don't think Brian's done a good job there. I think that's like scientific snobbery. Oh, well, there's proven physics. Yet we know through the history of time that proven physics has gone on to be disproven by new physics. And it's not a huge change you're asking for. And all we're saying is, look, perhaps this dark matter that we've made up to justify the equation is just made up.
Yes. It would be quite easy for them to disprove me. They would just have to produce some observations that I can't model. But they haven't done that.
Huh. I like I said, I think it might be what your model means in terms of the EM drive, because like I just know people don't want to accept the EM drive. I know it. I know. I mean, I remember it becoming a thing because I remember that the photo we saw of it, and I remember it kind of like being publicly debunked. Okay, can we just talk about dark energy quick? Is that more made up bullshit?
Yes. So,
fuck you, scientists. Fuck you, Einstein.
Yeah, the acceleration they've measured is...
Hold on, you're going to have to go back a step. So we've talked about dark matter.
Dark matter,
That's
yes.
basically made up stuff to justify an equation. What is dark energy?
So dark energy is the energy required to accelerate the universe away from itself.
Okay.
So by looking at standard candles, supernovae, they assume that these all explode with the same brightness. And they noticed that ones further away are dimmer than they should be, which implies that the universe is accelerating away from itself. And they've calculated this acceleration, and it turns out to be about 2 times 10 to the minus 10 meters per second.
Yeah, I don't know what that means. Sounds quick.
That's exactly the same acceleration that the Pioneer Anomaly had, galaxy edges have, globular clusters have, Proxima Centauri has. It's the same acceleration. So I can predict it very simply from my theory.
So they just made up dark energy. So dark matter is made up stuff that has to exist, but we can't measure or see it. Dark energy is...
Well, you see, the universe is incredibly massive. It's about 10 to the 53 kilograms. It's unimaginable weight, and it's accelerating away from itself. So imagine you see a
What do you mean by that? That it's expanding?
It's expanding, yes, but expanding at an increasing rate all the time. If it was just expanding, that would be fine. It'd just move away without energy. But
it's getting faster and faster.
That's right. So something is accelerating the universe.
That breaks inertia, because if it's expanded at a constant rate, that would be inertia.
Yes.
But
But
so it's the same. Is it fundamentally the same problem as galaxy rotation?
It is. Do you remember I said that I break Newton's first law?
Yeah.
So he said that things go at a constant speed, and I said, no, there has to be a minimum acceleration because, so you have these Unruh waves, and the slower your acceleration, the longer the Unruh waves get. If the Unruh waves are longer than you can see, they can't exist, according to this philosophy of Mach that I tend to follow. So this means you have to have a minimum acceleration. And it turns out to be this cosmic acceleration that they see, that they've attributed that they've invented dark energy to explain.
So if there's a small amount of acceleration, does that compound over time? Is that why we get the increasing? Because yes, it compounds over time. That's why it's accelerating. So there has to be some acceleration. There's a constant increase in the acceleration.
A constant increase in the velocity.
Yes, yeah.
So,
yeah. Okay. Because again, is that breaking relativity? No, that's breaking Newtonian's first rule of motion.
That's right. Yes, first law.
First law of motion. Okay. So the answer was there's dark energy.
Yes, they have to add energy to the universe to allow it to expand.
But it's dark energy because they can't see it.
That's right. Yes.
It kind of sounds like they're just making shit up. Okay,
but it's a very complicated issue because I actually don't think the universe is accelerating at all.
Oh, okay.
The reason they think it's accelerating is because the further away stars are, the more redshifted they are. So, you know about the Doppler shift.
Yeah.
That if things are moving away, things get wavelengths of sound get longer and light too. So they explain this redshift by saying that everything's expanding away from us, moving away from us, even accelerating. But in quantized inertia, the local physics depends on the size of the observable universe, the amount you can see. So stars further away are further in the past when the universe for them was smaller, and so the physics will be slightly different, which predicts a redshift that way.
Huh. Okay.
So now I haven't published this yet, but it's horrendously difficult to think about this particular one because all sorts of things get in the way. I mean, is the speed of light constant, for example? I don't know.
I thought the speed of light as a constant is proven.
That's a local constant. Maybe in cosmic time it has changed, but I simply don't know. All I can say is that quantized inertia predicts the kind of redshift that they see for distant stars.
Okay.
But I don't want to go too far into it because I haven't published this yet.
Okay, that's fair. Have you AI'd yourself?
Not myself, no.
Get up. So it's always fun to do this. I did it for myself the other day and it was a horrific experience for me, but for you it'll be different.
I have a feeling my son did it a few months ago.
Right, Connor, can you go into ChatGPT, ask for ask it if do you know Mike McCulloch's theory of quantized inertia? Is he spelled that right?
Oh, it's U.
It's
UWL.
UWL. All right. I always think it's a good base point to get it. Okay, yeah. So it's familiar. Explain what the coroid is. Key concept, Unruh radiation, horizon, inertia and energy, cosmological implications, predictions and tests, criticism and challenges. This is where it gets interesting. Whilst quantized inertia has gained some attention, it's met some skepticism from the scientific community. Some of the major challenges include lack of empirical evidence. One critique is that quantized inertia lacks sufficient experimental evidence and is not well supported by mainstream physicists as alternatives like dark matter or dark energy. Okay, so
but dark matter has zero evidence. Well, direct evidence. It's got zero.
Connor, ask. Okay, hold on. What's the second one? Theoretical consistency. Critics also point to issues in the mathematical formula of QI, especially regarding how well it fits in established framework like general. Okay, so we've established those are the challenges in the scientific community, that it's not competing well against something that's made up and unproven, but solves a math problem, and you're basically saying Einstein and Newton are wrong. You know, bold statement.
Well,
but...
yes, Newton is slightly
I love it, Mike. Fuck it. Fuck these people. Okay.
I mean, I admire both Newton and Einstein hugely. You know, I'm not trying to tear them down at all.
No, you're just better than them.
Well, no, I wouldn't say that either. It's just
I love it though. I want you to be right. I want you to be right just because I hate the snobbery of the physics community. Okay, Connor, can you ask it, is there any direct empirical evidence of dark matter or dark energy? I actually think it's quite fun to debate it with the AI. So it's quite good. As of now, there is no direct empirical evidence of the existence of dark matter or dark energy. Both concepts remain theoretical, but they're supported by a range of indirect evidence that strongly suggests their presence. Okay, so dark matter. Dark matter is hypothesized to explain the gravitational effects observed in galaxies and galaxy clusters that cannot be accounted by. Okay, so we've established that because of the galaxy rotation. Yeah, so it's a thesis that answers. Okay, gravitational lensing occurs when light from a distant object, such as a galaxy or quasar, is bent by gravitational field of another object. The bend in light can be stronger than would be expected from the visible mass. Again, it's a mass problem. They're just explanation. All these examples are all mass problems, right? There's a lack of mass.
Well, the CMB is a different one.
Okay, scroll up a second, Con. The pattern of temperature fluctuations in CMB is consistent with the presence of dark matter, which would have played a crucial role. But it's all based on a thing existing they can't prove exists.
Yes, and the CMB is very far away and very vague, and they fit their model using adjustable parameters to make it fit.
Okay, let's go on the dark energy one, Con. Dark energy is hypothesized to be responsible for the accelerated expansion of the universe. The evidence of dark energy primarily comes from the following observation. Okay, in the 1990s, astronomers discovered the distant type Ia supernova appeared dimmer than expected. This suggested the universe's expansion. Okay, but that's an expansion thing. Okay. Okay. Let's fuck with the AI for a bit. Okay. So just ask the AI, say, so you're telling me they have made up dark matter and dark energy as a way of coming to answering these problems, but there's literal zero evidence. All right, it's true that dark matter and dark energy are theoretical constructs that were introduced to explain. Okay. But sure, but there's still zero evidence. This is where it gets interesting. Yes, you're absolutely right that zero direct evidence currently exists for both dark matter and dark energy in the sense of actually detecting the particles of matter or directly observing them. The current evidence is all indirect based on observation of phenomena. Okay, so could there be alternate explanations then? Oh man. It does feel like there's a snobbery. Also, there's like a reluctance to say, you know what, this thing we made up, it could be wrong. Okay, yeah. So look, it's absolutely. While dark matter and dark energy are most widely accepted explanations for the phenomena we observe, there are indeed alternative theories. Modified gravitational theories. Is that the one there, MOND, that you mentioned?
MOND, the one I mentioned, yes.
Yeah. Okay. So we got MOND in there. Tensor vector scalar gravity.
That was an extension of MOND.
Okay. Emergent gravity. Eric Vernland. What do we think of that? What do we think of Eric?
I wrote a blog about that one. It doesn't work because he suggests that it's a question of scale.
Okay.
Not a question of acceleration, so
okay.
I discount that one.
All right, keep going. Modified gravitational. They didn't put yours in there.
No, they never seem to, but...
Okay, but what about... Ask it about...
Oh, there was a Wikipedia battle back in 2015. Myself and many of my supporters were trying to put up a page for quantized inertia, and it kept getting deleted by the editors.
Oh yeah, well, Wikipedia is wonk. What about quantized inertia? Quantized with a D. You'll figure out from that. Okay. So it knows about it.
But I have very strong direct experimental evidence because, as I said, this radius in the galaxies that the odd behavior begins is exactly the point where the Unruh waves become.
It's got more evidence against. Go up. Well, more arguments. So again, lack of empirical testing. Fine, we'll test it. Compatibility with general relativity. Well, Einstein could be wrong. Limited scope. It can explain certain phenomena. It may struggle with others, such as detailed behavior of galaxy clusters, gravitational lensing, or exact measurements of the cosmic microwave background. Is that fair?
I haven't. That's true. I haven't looked at gravitational lensing or the cosmic microwave background yet.
Is it on your to-do list?
It is, yes, but I've got quite a long to-do list.
Yeah, I can imagine. Theoretical basis. Some critics argue that the theoretical basis of QI is not as robust as other mainstream theories like dark matter or general relativity. The idea of modified inertia due to space-time horizon and quantum effects of the Planck scale is still speculative and not yet fully formalized into a predictive and mathematically rigorous framework. It feels like this deserves more people looking at it. It feels like.
Yes, I mean, thousands of people are working on general relativity. With me, it's just me and a few other people helping, like Xiaomei Jine and others like that.
Few rebels. So, talk to me about solar luminescence.
Oh yes, okay. So, that is a phenomenon where you have a glass sphere, and you have water in it, and you have a bit of argon, I think, as well, usually. And you inject sound into it, and a bubble forms in the center, and the bubble collapses. And every time it collapses, it emits massive amounts of light. And, well, there are various theories about why it works, but
this is proven and seen.
Yes, okay. This is well understood, but it's well observed, but it's not well understood. Nobody knows why it happens. But I think this is related to things like cold fusion, and it's related to Heisenberg's uncertainty relation. As I was saying, as you study smaller and smaller regions of space, you get more and more quantum foam. More certainty of position gives you less certainty of energy, and so as a bubble collapses, it confines a region of space, and so you're bound to get energy from it, in my opinion. So you'd get these flashes of light, and I can predict the heat that you get from it. So it there's also another way to think about it. I'm trying to think about quantized inertia in terms of information. So I'm trying to reformulate the entire theory in terms of information, because I've noticed that I can derive it that way. There's something called Landauer's principle, and he noticed that whenever you erase a computer's memory, you're erasing some real pattern, like 0 1 1 0 1 0 1, something like that, and you're making it all 0, and that represents a reduction of entropy. And I don't know if you've heard of the second law of thermodynamics, that entropy must always rise. Things get more complicated.
Yep.
Like a teenager's bedroom or something like that.
Yep.
So when you erase a computer memory, that reduces entropy, and that can't be allowed. So heat must be produced. So this suggests to me that the destruction of information produces energy. So, and I think this is what quantized inertia does. It brings information into physics. So, because at the moment, mass and energy, their combination is supposed to be conserved. But I think what's actually conserved is mass, energy, and information. And you can convert information into the two other things. And and I can derive quantized inertia this way. So if you think about this accelerating object, it's accelerating to the right. Suddenly it sees this horizon here, because information can't get to it from behind that horizon. This blocks out the rest of the cosmos here. And if you assume that each Planck length is a bit, and you work out the amount of energy you get out, it's exactly the energy you need to produce the inertial mass to pull the object back. So it all works very nicely. So this suggests that we can get energy from information, which is a new source of energy.
Don't we get when things go into a black hole, they erase information.
Yes,
Don't we get energy from that? Isn't that what
that's what
Einstein radiation is from that as well?
there's Hawking radiation.
Hawking radiation.
You're right. That's one of the big questions of physics. There was a so-called black hole war between Hawking and Roger Penrose, and Gerard 't Hooft and some other people. And Hawking reckoned that information was destroyed by a black hole, by the horizon, and 't Hooft reckoned it wasn't. And Hawking conceded, actually. He said, okay, you win.
What do you think?
I think information is destroyed. I think information can be destroyed and energy can be produced.
Is the destruction of information relative? So us outside the event horizon, the information's destroyed for us because we can't see it.
That's
but
right.
If you travelled alongside something else and hit the event horizon at the same time, it still exists over that event horizon for us because we can still see it because we're with it.
Yes, that's a good point. Yeah.
Yeah.
I think that's right. But so I'm on Hawking's side with regard to the black hole information war.
So ironically, it's relative to where you are. Okay, let's right. We didn't properly do the EM drive. So under your model, the EM drive is real.
Yes.
How does it work?
Okay, so the EM drive is a conical metal cavity, and microwaves are put in, about 2.3 gigahertz, something like that, and they make accelerations and the metal wall vibrate, a lot of radiation accelerating electrons, and these produce Unruh radiation. So at the narrow end, fewer Unruh waves can exist because yes, it's like when you go in a bath, you can make certain waves by playing around. But if the bath is smaller, there are fewer wavelengths that are allowed within the bath.
Yep.
So at the narrow end of the M drive, there are fewer Unruh waves. There's less inertial mass, and at the wide end, there's more waves allowed, and there's more Unruh waves. So now, if you consider a photon or anything moving from one end to the other, every time it goes to the wide end, it gains inertial mass, and every time it goes to the narrow end, it loses it.
Mm-hmm.
So to conserve momentum, the thing has to move towards the narrow end. Another way you can think about it is that the narrow end damps the quantum vacuum, the Unruh field, more because it's closer together than the wide end. So it produces a kind of void in the vacuum at the narrow end, and so it falls down, is pushed towards that void. It's sucked towards it. I don't know if that makes sense.
Yes, as to an extent. And so, here we go. So Con's got
Yes, there we go. Yeah.
Larger force, net radiation force for our smaller force. The simplified schematic drawing of an M drive prototype by Tajmar and Fielder. Who are Tajmar and Fielder?
Oh, Tajmar is an experimentalist who tested the M drive.
Yeah.
After Scheuer claimed it. Scheuer claims that Tajmar did not do it correctly.
Okay. Because
NASA,
is that because it didn't work for Tajmar? Then
Scheuer claims that he didn't use the resonant frequency of the M drive. So NASA also tested the M drive and got a positive result.
What?
So,
hold on.
Yes, Harold White at EagleWorks, NASA, they tested it and they published a paper which took them ages to publish, actually, but they did.
And how has that been accepted?
Well, it's interesting that people tend to believe Tajmar over NASA with it.
Do you think it's this kind of like this reluctance again to accept the idea?
Yes, I think that's right. Yeah.
NASA's impossible space engine tested. Here are the results. Spaceflight is hard. Blasting heavy cargo spacecraft and maybe people to respectable speeds over interplanetary distance, not to mention the luxury of stopping at destination, requires an amount of propellant too massive for current rockets to haul into the void. That is unless you have an engine that can generate thrust without fuel. Okay, so we know how this works. But scientists at NASA's Eagle West laboratories have been building and testing such a thing called an M-drive, the physics-defined contraption ostensibly produces thrust simply by bouncing microwaves around inside a closed cone-shaped cavity, no fuel required. Okay, right. Han Solo, head button. We can... Okay, so what did they find? The thrust is not coming from the M-drive, but from some electromagnetic interaction.
That was Martin Timar's test.
Okay.
As I said,
Okay, yeah, sorry. So the group led by Martin Timer of the blah, 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 tested the drive in a vacuum chamber with a variety of sensors and automated gizmos attached. Researchers could control for vibrations, thermal fluctuations, resonances, and other potential sources of thrust, but they weren't quite able to shield the device against the effect of Earth's own magnetic field. When they turned on the system but dampened the power going to the actual drive, so essentially no microwaves would bounce around, the M drive still managed to produce thrust, something it should not have done if it works the way NASA team claims. Researchers have tentatively concluded that the effect they measured is the result of Earth's magnetic field interacting with the power cables in the chamber, a result that other experts agree with. Surely they can find a way of doing the test where that doesn't. Okay, so perhaps even more powerful tests would what the space doctors ordered help settle the debate. I don't think that article... Yeah, it's not the best one. But NASA... Okay, so NASA proved it, but they think it's the gravitational pull on the wires.
NASA showed a positive thrust, but Timar looked at it and I think he claims that there's a Lorentz force on the wires.
So where are we in the world of M-drive? Is it just people just not bothering anymore, or is people still working on it?
People are a bit scared to approach it, I think, now.
Because they'll be ridiculed?
Yes. It's interesting that humans have this tendency to not believe things that don't have a theory behind them. It should actually be the opposite way around. You should look at the observations and work out the theory. But
well, that's science, right?
Yes, but it's not what people habitually do. That's why scientists are so unusual.
At Ledden, we built the best Bitcoin-backed loan platform in the world. Proven, trusted, growing. Ledden's proven track record speaks for itself. Visit ledden.io/Mr. Obnoxious to get started. Ledden, there is no second best. Ledden is not regulated in the United Kingdom. Any credit products or virtual asset services provided by Ledden are not subject to UK regulatory protections. Please consider the risks associated with virtual assets and consult a financial advisor before making any decisions.
But I found a better way to do it, to do the same thing. And it was actually suggested to me by 2 engineers in California after I got the DARPA funding. They said, why not a capacitor?
That sounds like something from Back to the Future.
Oh, a flux capacitor.
Yeah.
Yes, okay, well, it's different to that. It doesn't involve time travel. But yes, Frank Becker and Anker Batt from California, they suggested a capacitor, and they tried it with a bit of liaison with me, and they saw a thrust. And I can predict that as well. So I could explain how that's predicted. So if you have a capacitor, so it's 2 metal plates very close together, and in this capacitor you make electrons jump across between the plates. You have to set it up so there's a large potential difference between them, so the electrons, when they decide to jump, they do it incredibly fast, so the acceleration is very high. So this is the interesting thing about quantized inertia, that it works in the cosmos when the accelerations are very low. But if you make a small cosmos, like a capacitor cavity, then the acceleration at which it works can be high. It depends on the scale of the universe you have. So if you make the electrons jump across at this huge acceleration, Unruh waves will be formed to produce an inertial mass, but these Unruh waves will be damped by the plates. So the electrons will have less inertial mass than you expect. So to conserve momentum, the cavity has to move in the same direction that the electrons are moving. So the quantized inertia predicts this very well. I made a prediction and then they tested it, and I guess I could show you the graph. If you look for archive, so ARXIV, Becker and BHATT, the results are really good.
Becker, sorry, spell that again.
Yeah. So Becker, Becker, and Bat, Bhatt. Yes, that's it. If you can go to the PDF at the top right, view PDF. So that graph shows the separation of the plates along the x-axis, and the force they got in newtons up the y-axis. So as they brought the plates together, the force went up exponentially fast. And I made a prediction, and I mean, you could find it online perhaps, but it agrees exactly with the curve they got there without any tuning.
So the implications of this are?
So this is an easier way to produce the M drive and propellantless propulsion.
Have you spoken to these guys?
Yes, yeah. They emailed me to say they liked my papers and why didn't I try a capacitor? And then they tried a capacitor and it worked. And then a US company called Ivo Limited, led by Richard Mansell, they decided to try it in a vacuum because people complained that it might be an ion drift problem because of air. So he and his company tried it in a vacuum and they found the same result. And then I tried it at Plymouth. I set up a lab and tried it at Plymouth University with DARPA money. And then last year, Ivo launched a test into space. They launched a CubeSat with a capacitor on it. But unfortunately, the satellite was lost before they could do the test.
That sounds suspicious to me.
Well, I don't know. But
Colin, can you just scroll up to the very top? Is there like an overview? I just want to read what it says at the very first page. Okay. What's the title? Electrostatic accelerated electrons within symmetric capacitors during field emission condition events exert bidirectional propellantless thrust. Okay. During the internal discharge, electrical breakdown by field emission transmission, thin symmetric capacitors accelerate slightly towards the anode, an anomaly that does not appear obvious using standard physics. Various thicknesses of discharging capacitors have been used to demonstrate and better categorize this phenomenon. It was observed that it is possible to reverse the force by adding conductive materials in the immediate proximity of the cathode when physically separated from the anode, thus galvanically connected. Conversely, the addition of conductive materials in the area surrounding the anode did not alter the original force observed. The data gathered seems to confirm a phenomenon that could be exploited for propulsion purposes, in particular fuel-less applications in a vacuum. The results could be correlated to an external cause which appeared to be influenced by the particle's acceleration. Overall, the preliminary results are encouraging for practical engineering purposes. Peer reviewed?
No.
But
So I'm writing
out there.
Yes, it's on the archive.
Okay.
A place I've been banned from. So.
Oh God. With all this stuff, everything you learn and everything you've been down, has this changed your any fundamental ideas or thoughts you have about the nature of our universe and life and existence? And
yes, well, it's convinced me that, well, the universe looks very much like a simulation because I've managed to derive. I can derive my theory by assuming that the universe is like a processor.
Connor doesn't like this theory.
No, I do. It just scares me. Because it means nothing means anything.
We're all just...
Not necessarily. It doesn't mean that we're in necessarily that we're in a game. So what tends to happen to science is that as we develop new technologies, like machines for Isaac Newton, physics tends to follow to some extent and improve itself that way as we make little universes by ourselves, like machines or now computers. We see how they work, and so our physics adapts and improves partly following the technology. It doesn't mean that the universe is a simulation. It just means it's behaving like it.
Okay, behaving like it, or do you think it is?
But in science, we're very careful not to step beyond the bounds of what we can actually say.
Okay, what are the bounds of what you can... What is your view? We're acting like a simulation.
Yes, that the universe is behaving as if it was a simulation, because
Wouldn't a universe even if it wasn't a simulation, it would have to behave? Or is there something specific that makes it feel like a simulation?
the way I covered this in my book, the way I think the universe developed was from randomness, complete randomness. But if you have a completely random situation, then occasionally, like in the game of life, you'll get processes that repeat. And as soon as over millions of years you get a process that repeats, it's going to repeat forever, isn't it? So eventually you end up with a universe that has a load of repeating processes in it. And that's what we see. We see orbits, and we see life repeating itself as well. So I think it's kind of inevitable.
Okay, probably should ask you, in your world, what if I ask you to define simulation? Because in simulation theory, the idea is that we're just like a game or a computer that's been switched on. You know, the fundamental idea is that if with advanced technology, the advancement of computers over time will have enough processing power to simulate life, and therefore, if we can, we'll do it millions of times, and likely this is just an advanced game version of Fortnite.
But I can't. I mean, that's going into theology, really, and I can't step beyond the point of saying it just seems like a simulation. It behaves like one. But computer games recently have given me some insights as well. For example, I can derive special relativity and probably general relativity by assuming that it is a simulation. And I haven't published this as a paper yet, but what gave me the idea was I was playing Minecraft with my son, and he built an amazing city with lots of villages in it. It was taking a lot of processing power. And every time you approached the city, the processing of the game slowed down. Just as happens to time in our reality when we approach a massive planet. In general relativity, you've seen Interstellar.
Yeah.
When they go down onto the planet, time slows down, which Einstein attributed to esoteric, abstract concepts. But I think it's processing time, because I can get the same equations by assuming it's simply processing time.
Wow. That's wild. So this simulation doesn't have enough RAM.
Yes, well, it's limited. It's limited in its...
That's wild. Does it make you think about the nature of life and your role within the world?
Well, yes, it does. I mean, I was going to write a novel about it. Actually, I tend to write novels about things as well.
You've how many novels have you written?
I've written a couple of short novels.
Are they sci-fi novels?
Yes, science fiction.
Are they published?
Yes, they're published on Amazon. I self-published those.
Okay, tell me about the two you've done.
Yeah, so I've done Falling Up.
Yeah.
Which is about consequences of quantized inertia for quantum launch, using the capacitor, things like that, M drives to just launch into space.
But it's a novel, so is it the world where it's been applied and used?
Yes.
Yeah.
Yeah, so it's at the time I was working at the Met Office, and I had to do a lot of my work just in my own time, and it wasn't what I was supposed to be doing. So it's kind of about that, about somebody who's got the solution but can't actually publish it.
It's like autobiographical.
Yes, sort of. And then there's Hacking the Cosmos, which is my second novel, which is about the possibility of how to make a portal. So as I said, I'm a very strong follower of Ernest Mach's philosophy that if you can't see something, it doesn't exist. So in a novel, I work out a way to not see a portion of space. You can bend light away from a portion of space so you can't see it. Therefore, it doesn't exist, so you just step over it. So you can step over to Mars. You can delete the space from here to Mars and just go there.
Okay.
So it's about that. It's supposed to illustrate this philosophy that if something can't be seen, then it doesn't exist.
Is that related to that idea within quantum mechanics whereby something is a wave of a particle and you don't know what it is until you look at it, or it can change?
Yes, yeah, it's similar to that. Yeah, Schrodinger's cat.
Yeah.
But it's
both until then.
It's deeper, really. I mean, if you look at the history of science, science has always progressed when people, for some crazy reason, have said, let's only put into theories what we can see. So, for example, the first scientist, Thales, he, instead of putting gods into theories, he said, why don't we use water? So he said everything is water, which was wrong, but it became testable. And he was the first scientist. And then Descartes, later on, he had all these invisible vortices in space whirling things about, but Newton said, let's only put in things we can see. So he had the planets themselves and gravity. And then Einstein himself did it, because special relativity is based on that idea that the speed of light is something we can actually measure, but space and time are not. So speed of light is the rock, if you like, and space and time, you can just play around with them as you want.
And so the new novel, the third one?
So there's only 2 novels.
Oh yeah, but I thought you said you were going to work on a new one.
Yes. Yeah. So in the new one, where we're sort of, I'm not sure I should say really.
You want to save it?
Yeah, I might save it because it's quite a shocking thing.
But now I want to know. Will you tell me after the show?
Yes, yeah, I'll tell you after the show. Yeah.
I know people are going to write to me and they're going to like, Pete, what's it about? I'm saying I'm sworn to secrecy by Mike. Do you think much about the creation of the universe? Because simulation or not, if it's a simulation, the very first one still had to be created. Because this is, we were saying in the lift on the way up. The most important question is like, kind of how and why. How can out of nothing something come with all these rules that are established? And it just fries my brain, Mike. Fries my brain.
Well, of course, I don't know, but
no.
what I said a bit earlier is what I think that, as Heisenberg said, as you focus on smaller and smaller regions of space, you get these random particles coming out, and if you have a random field for long enough, you'll get repeatable patterns forming, and once they form, you start to see things like particles and matter and planetary orbits, which are repeatable patterns, and then life eventually. So,
right, before we scan this, is there anything on this that we've not covered yet? The bits that I've not asked you about that I should have?
I suppose the possibility of that it allows interstellar travel, which is...
Oh yeah, I mean, we should probably cover that.
Yeah.
How?
Well, the problem with getting to the nearest star at the moment is you need to go half the speed of light. So
that's
with
Proxima Centaurian.
That's right, yes.
Yeah.
So you need a huge amount of fuel to get up to that speed, about the same as planet series, planet-sized amount of fuel, which isn't feasible. And also, that would increase the amount of fuel you need, so it's a catch-22 thing. The advantage of having a thruster like the capacitor thruster or the M drive or one of these kind of thrusters is that there is no fuel. You just need power. So I've designed a spaceship with some engineers helping, like Kelvin Long.
Okay.
And it turns out you can get there in about 15 years.
Okay.
Using this propulsion system.
15 years for the people on the spaceship? How many years for the people on Earth?
Yeah, it doesn't change much, actually, because we're only going about half the speed of light. So,
okay.
Yeah, but it's a year or two difference.
Does the spaceship get us off Earth? Do we have to use traditional thrust to get into space and then activate it?
Traditional thrust to get off.
Yeah, so. because with the force of gravity against us.
Yes, that's right.
Yeah.
But I think eventually we'll be able to quantum launch with this system, because quantized inertia predicts that if you can get capacitors with the plates very, very close, then the thrust will increase an awful lot. So it should be powerful enough to produce launch eventually.
And when we do, if we get this, would it be as we observe a spaceship taking off, a very different experience? Would it just
Yes, it would.
look like sci-fi, just almost a bit like, you must have seen Arrival, the film Arrival.
Yes, it would look like that.
Yeah, and could stuff just balance in the air and move in weird ways that we're not used to?
Yes, and this will sound crazy, but I think you'll be able to design buildings that float. Because you could design a building that has a nanostructure within it that damps Unruh waves more above than below. So it's got a gradient in it. So it'll have an Unruh gradient which will continually push it upwards. So you could have
all this stuff with the UAPs, all the talk about UAPs, and it's like a more accepted possibility that we've been visited by aliens. Are you following any of the UAPs, like the Tic Tac and if any
I
of
was
that?
interested by the Nimitz event. I thought that was quite interesting.
Which one's that?
The USS Nimitz. They saw the Tic Tacs,
yeah,
and
the Tic Tac.
The fighter pilot pursued them.
So the way they moved was unconventional. It didn't conform to conventional physics. And so when you see something like that, do you think of the work you're doing? Is it comparable?
Yes, it looks, if they're real, it looks like that. I mean, I can't decide whether it's a government psyop or whether it's real.
Well, so when I did my interview with Matthew Pines, that's what I said. I said, either this is a psyop or the aliens are here. Like, it's one or the other. Like, there's no middle ground for me. And I can't work out the thesis. I can't work out a credible thesis for the psyop.
But they do look like they're using quantized inertia. The great thing about quantized inertia is if you hugely accelerate in a spaceship with quantized inertia, there's no whiplash. You don't get thrown around. If you accelerate one direction, you get thrown against a wall unless you've got a seatbelt.
Yeah.
That won't happen with quantized inertia. So you'll be able to accelerate as much as you want.
Why is that?
That's because normally you accelerate with a rocket.
Yeah.
So a horizon appears behind you and pulls you back against a wall, hurting you.
Mm-hmm.
But with quantized inertia, what you do is you damp the Unruh waves in front of you to move yourself forwards. But the gradient would be the same for everything in the ship.
Okay.
So your acceleration would be same as the whole. So,
is there is it very hard? It seems it's very hard for novel, unique ideas in the world of physics to gain credibility.
Yes, it is. Yeah, and I expected that. Really, it takes decades usually. In fact, the original idea of inertia was proposed by Philoponus in 500 AD.
Okay, so it takes centuries.
Yeah, it took 1100 years for Galileo to say, "Oh yes, okay, that sounds sensible."
Okay, look, this is great. I think it's fascinating. I'm not the person to say whether it's real or not, or legitimize it, delegitimize it. I just think it's fascinating to talk about. I think everything like this should be talked about. I find it fascinating that we have a fully accepted model with dark energy and dark matter, which is entirely unproven. We're just saying there's this stuff we can't see or prove exists, but that solves our equation, so we're just going to accept it. Whereas I think you have a model and a thesis that is provable and people are pushing against it. I find it fascinating. I hope you continue. I kind of want you to be right, because we'll be talking about you in centuries alongside Aristotle and Newton, Einstein and McCulloch. It'd be pretty cool, wouldn't it?
Well, yeah, we'll see. I never know what to say when somebody says something like that.
No, we'll see, man. But listen, just keep doing your work. Fuck these people. Even if they say no, just keep doing your thing. I mean, there's people who find it interesting. I think interesting ideas should be discussed. I think interesting ideas should be investigated. I'll be interested to follow your journey and see what people say about your work. I'll definitely keep an eye on it. And it's been a fascinating 2 hours talking to you, and I wish you all the best with it.
Well, thanks for inviting me, and I hope it makes sense, and
we'll see what happens.
Yeah.
I would say I'd read one of your papers, but I don't think I'd understand it. I'd just rather talk to you. Maybe have a beer next time. Mike, great to have you. Thank you, everyone, for listening. See you soon.